Welcome friends, let us study the concept of relative stability in frequency domain. So in this session we shall learn the topic of relative stability. Mainly we shall focus on relative stability in the frequency domain, parameters of relative stability, position of roots and relative stability, how they are connected, and we shall understand different concepts of positioning of poles or roots or zeros through illustrations. So let us start with the definition of relative stability. So a relative stability of a linear time invariant system model may be defined as the margin by which the system may be perturbed or disturbed, or its parameters may be varied before the system approaches the verge of instability. So this definition seems to be a little longer and complicated, but let me express this definition in a simpler way, that whenever we are having a system, so we can analyze the system in frequency domain by different tools like polar plots or Bode plots, or some other tools are there we'll learn in coming lectures. So when we are using such tools, we can visualize that with the variation of frequency, the gain of the system changes. So as in polar plot, we can see that a system will have a gain crossover frequency or a phase crossover frequency. Accordingly, there will be some margins of stability, that is the phase margin and gain margin respectively for gain crossover frequency and phase crossover frequency, and these margins will basically define about the system ability to absorb or defend the system against any external disturbance, whichever be the situation. So whenever we are designing a system by frequency domain analysis studies, we can say that in case of external disturbances, if there are change in the gain of the system, how much the system can tolerate such an unwanted situation. So such things will be analyzed more by the dint of relative stability. So let us first write a definition. So definition of relative stability is relative stability of relative stability of LTI, linear time invariant system model. I always speak that these are all models. Model may be defined as the margin by which the system may be perturbed, perturbed means disturbed, or its parameters may be varied, So parameters could be the coefficients or the stability parameters. It can be a wide range of parameters. So its parameters may be varied before the system approaches the verge of instability. The verge of instability. So this is a very comprehensive and well expressed definition of the relative stability of the system. To understand this concept, let us draw the polar plot of a sample system. So I am drawing the polar plot of a sample system. I am taking G at S, H at S equal to 1 by S into tau 1S plus 1 into tau 2S plus 1. So I believe that you can recap what should be the pattern of polar plot. In this case, this is real part of G at J omega, H at J omega, and this is imaginary part of G at J omega, H at J omega. So we can have a polar plot of this. Let us do it very carefully, because the practical situation will give a very different result if we don't plot it properly. So I give this point as -1. So you can see that I am drawing the radius of -1 over here. So this is the frequency of omega crossover gain. So omega gain crossover frequency, so magnitude is 1. So this length should be should be 1 in magnitude, and the other important frequency is this one. This is omega phase crossover frequency. So this is crossing the point of -180 degree. Now whenever I am crossing the different frequencies, the system will show different dynamics. So let me say that this is the frequency, starting frequency, and this is the closing frequency. But whenever I am running a system in real time, the flow of the system in time domain will be in this direction. So we'll start from very high frequency and we'll settle down at very small frequency. So to understand this, let me draw the time domain response. Let me draw the time domain response for the same, so that things are clear for you. So I have the time axis over here. This is the time axis, and this is the gain of the system in time domain. So we can say that the system gain in time domain is magnitude of gt ht in time domain. So this is the magnitude, and suppose I am giving a step input to the system. So the step input should be like this. This is normalized input and output 1.0, and how the system will respond to this. Let us draw it. So we can say that a system may have this kind of response. maybe like this. So in that case, we have to see that the direction of the flow in time is like this, and the same direction I can see in the frequency domain as this. So this you can say that here I have omega tends to infinity, and here I have omega tends to 0. So you can correlate these two frequencies, how they are connected to each other. So this point is corresponding to this point, and this point is corresponding to this point. So you should be careful about the plots, how in the time domain the system will respond, and the same time domain when it is mapped to frequency domain, how the system will respond. So in that case, whenever the system is starting from an initial frequency of omega tends to infinity, that corresponds to the origin of the polar plot. So once you start from the origin, and depending upon the kind of system, you will get different gains of the system, because initially when there is input to the system will gradually try to follow the forcing function, that is the input. Suppose in that case it is 1.0, so system will try to follow this. So because of that there could be overshoot. But in case of the system when there is some other frequency like resonant frequency or resonant gain, then the overshoot may be very high. So such an overshoot may be detrimental, and system may go to the verge of instability due to such overshoots, which are caused by the resonant modes or resonant gain of the system. So to overcome the situations like this, we need to have the complete study of the system, especially in its transient mode. So when it is in transient situation, transient phase, basically you are starting from here, and maybe you can take it as the bandwidth. So I'm saying that from here starting up to the bandwidth of the system, you will say that this is the transient phase of the system. So we need to study the range very carefully. So for that, the parameters we need to analyze are like this. So the parameters of relative stability. So parameters of relative stability. What are the parameters of relative stability? Let us check one by one. First is resonant peak. So resonant peak we represent by MR. The second one is resonant frequency. Omega R. So third one is bandwidth. So we can say this is omega B, and this can also be said as the gain crossover frequency, that is your omega crossover gain, or corner frequency omega c. Then the fourth one is gain margin GM, then the fifth one is the phase. We can take because for phase margin we have gain crossover frequency. This is the gain crossover frequency. Similarly for phase margin we have the phase crossover frequency, so we have the phase crossover frequency. So this is crossover phase, then this is, so gain margin will be obtained from the phase crossover frequency, and phase margin PM will be obtained from the gain crossover frequency, like this. So with this we understand that all these 6 parameters are the parameters of relative stability, and let us now understand that why we are saying that the system is relatively stable for the transient phase. So we can see that the polar plot, the time domain response, and the placement of poles in the S-plane can be related if we can study the responses thoroughly. Therefore, I would like to draw the polar plot, time response, and placement of poles on the S-plane simultaneously. Let me draw the polar plot first. So this is the polar plot, real part of G at j omega, H at j omega, and here you have imaginary part of G at j omega, H at j omega. So I am trying to use the same polar plot for the sake of simplicity, because we have the system in real time. The control systems are low pass filters, so we have the gain in high frequency which is very less. So this is the -1 point on the negative real axis. Then this is the origin where the system will be observed at infinite frequency, and here we have omega tends to 0, which is actually the ending frequency. So when in time domain we move, the movement is like this. So I place here the time domain response of the system for a step input, maybe like this. So I'm taking the simple example of two situations in S-plane, where we have the poles on the imaginary axis and where have poles on the real axis which are away from the imaginary axis. So I can write like this: the poles on the real axis away from the imaginary axis, this is the j omega axis, this is the sigma axis, here again j omega axis, here again sigma axis. So for this case, suppose we have the poles near the imaginary axis or on the imaginary axis, that is the complex root. So In case we have a nominal system where the poles are away from the imaginary axis, or even there is no pole on the real axis, so we are away from the imaginary axis. In this situation, if I draw the polar plot, we'll see that the system will be a nominal system like this, and in case of external perturbations, we see that two situations of external perturbation I am taking: at the phase crossover frequency, omega crossover phase, and at some other frequency, we see that in case of some external disturbance to the system, there is a modification in the magnitude or gain of the system. So the plot will change its dimensions in this radius. Within this radius, it can change its dimensions. While at high frequency, if the external disturbance is added to the system, again the system will change its dimensions. But you can see that we have a bigger radius of tolerance, while the distance from the point to the minus one point on the real axis is a longer distance. So this I can consider as B1, this is A1, here this is A2, and this distance is B2. So in case the frequency is less, we can see that A1 is greater than A2 and B1 is greater than B2. It means the margin of stability of the system increases if the frequency reduces, that is, the system is crossing the imaginary axis, system is crossing the set point, going to overshoot, then reaching the set point. So this phase is the transient phase, this is the transient phase. So once this phase is crossed, so we are reaching a frequency range where the frequency of the system is less, and for this range, if there is some external disturbance or uncertainty can be tolerated with higher stability margins, because you can very much understand that both the gain margin and phase margin will be better for this situation. You will have the better gain margin and phase margin. So we understand that near steady state of the system, the external disturbance can be tolerated with better stability parameter. At the same time, I say that if there are poles on the imaginary axis when the system is reaching the low frequency region, at that time the presence of complex roots of the poles will cause the system to be more vulnerable to instability, because this is the situation I am telling about. The oscillation due to the presence of roots on the imaginary axis can be viewed like this. Oscillations can be viewed like this. You have the set point and the system is reaching the steady state, and then there is sustained oscillation in the system like this. So that is equivalent to the case here. We can say that the plot will be having a bigger sense of magnitude variation because of this sustained oscillation near steady state or zero frequency, because of which the margin of stability will reduce. So we can understand that if the roots are on the imaginary axis, then the margin of stability can be correlated with the situation. So if there is a polar plot and we have roots, so you can see that because of these roots we can have a bigger impression of the plot like this. So because of this we can see that the margin of stability will reduce. So similarly, if the poles are away from the imaginary axis, like this is the case, then in that case the system will die down faster. So as we can say that for this situation the system will die down faster in time domain. So if there is, suppose this is the case of A3, this is the case of A4, so we can say that farther is the root from the imaginary axis, faster it will die down. So this is the case for A4 and this is the case for A3. So in that case again we will see that the margin of stability will be better, like we have seen on the polar plot. A system with its most dominant roots, which are the slowest, with its distance from j omega axis in S plane defines its ability to maintain stability in case of uncertainty in system dynamics, or parameters, Further, the root sorry, it should be further the root is from j omega axis, more is the stability margin, and faster the system will achieve its set point, and faster the system will achieve its set point. So in a nutshell we can say that if the roots of a system are away from the imaginary axis in S-plane, then the system response will die down fast, the transient will settle down fast, and thus the relative stability of the system will have more stability margin. So this can be compared by drawing the S-plane and placing the poles of the system and seeing how the response will be in time domain, and then checking the response of the same system in frequency domain using polar plot as we have done today. In the same way, we can find out the system responses for the Bode plot also, where we can see that for the case of system responses of the poles placed near the imaginary axis and away from the imaginary axis will have different responses, and for that stability margins will be different. So with this we wrap up with the relative stability parameters in the frequency domain, and in the coming session we'll start learning about the Routh-Hurwitz stability criteria. So in this video lecture we have discussed some stability related topics and the effect of parameter changes in the system, and again the impact on the gain and phase margin with the pole placement on the S-plane. In case you find any difficulty understanding certain points of the topic, you can definitely ask me through my email ID. This is controlsystemsfaq@gmail.com, and my students can send me WhatsApp message or call by phone as well. So if the lecture is useful for you, please like this video and subscribe it and set the bell icon in case you have not already subscribed the channel. So this much is for today. Thank you for your patient listening.